Welcome to the AIA structural exam modules. This is module 7. We'll be talking about stress calculations in beams. So let's get started by doing a little basic review on what we mean by stress and by strain. So when we're calculating stress by definition, I'll use the notation sigma, is force divided by area. So going back to some basic strength of materials, if I were to take a piece of steel, rebar, I put it in a load specimen testing machine, and I pull on it with a tensile load T, and I graph that relationship of the stress in that rebar by its deflection. And for the purposes of this graph, we'll define what we mean by strain and by stress. So the stress is going to be T over A, the tensile force, divided by the net area of the rebar. The graph, and this is only for steel, is going to look like this. It's going to remain linear to a certain portion. The deflection of the bar, as the bar continues to deflect, delta, is measured by what we call strain. Strain is measured using the term epsilon, which is delta divided by the original length. Delta is the deformation of the bar. L is the original length of the bar. And so this is called strain. Stress and strain. So the stress-strain curve looks something like this, and it reaches a magic point here, which we call the yield point. And this is called the yield strain. At that point, the bar begins to deflect substantially more, and a lot of fundamental properties in the bar changes. In simplified terms, the bar, once it passes the yield point, will never go back to its original condition. Everything on the left side of the yield point is called the elastic zone. Everything to the right of the yield point is called the plastic zone. And the reason is that if I stress that bar past the yield point, it will never return to its original condition. If I were to stress it up to this point and release the load, it will deflect back to what we call a permanent offset. It'll be permanently deformed. So the yield strain, what are the typical values for steel? Steel, like all materials, has specific properties. The slope of this portion of the curve, which is called E, E is the modulus of elasticity. Sigma yield point, normally referred to as F sub y, is the yield stress. For steel, remember we're only talking about steel now, E is normally 29,000 KSI, or 29 million PSI. The yield stress normally 36 KSI, or 36,000 PSI. That's for a grade 60 steel, that's for a grade 36 steel, also known as A36. We also have grade 50 steel, in which the yield strength is 50 KSI. And then we have grade 60 steel, in which the yield strength is 60 KSI. This is normally used for rebar. This is used for structural members. But in all cases, the E value is constant. It's always 29,000 KSI. That never changes for steel. So going back to our example here, let me label my sheets. Page 1, module 7, and then we have page 2 for module 7. So going back to our basic understanding, that's our measurement of tensile stress. For bending stress, we use some simplified formulas. I won't bother to derive those formulas for you, but only to show you how to use them. For bending stress, we simplify the beam as behaving in a certain fashion where the beam will deflect with plane sections remaining plane. What that means is that in our calculation protocol, we define an axis in the center of the beam, which is called the neutral axis. The neutral axis, NA, is basically a zero stress line. You'll see what that means in a moment. If I apply a load to this beam, plane sections remaining plane means that the beam is going to deflect with a certain level of curvature so that the neutral axis always remains perpendicular or 90 degrees to this bending section. This is the neutral axis, and the definition of the neutral axis is the zero stress line, which means that along that axis we're having zero bending stress. So if I did a free body diagram inside this section and I cut it out, originally the section which was undeformed, now as it goes through deformation, bends like so, like a pie. And my bending section, my neutral axis, is the zero stress zone. And the way that it's bending is I'm having compression on the top and tension on the bottom. And so if I graph my stress profile is a triangle. So I'm not going to go through the math to derive the equation. I just want you to understand where this comes from. So here's my neutral axis. Here's my stress profile. Compression on the top, tension on the bottom, and the formula for the stress, sigma, or normally we use F sub B, is capital MC over I, or also known as M over S. Let's define what those terms are. The moment divided by the section modulus. So my stress, FB, which is MC over I. M is the bending moment. C is the distance to the extreme fiber. I is the moment of inertia. So if I look at a cross-section of a steel beam, a very typical steel beam, we'll make it a wide flange I-beam section, which looks something like this. I'm symmetric about my x-axis. C is the distance to the extreme fiber. I is the moment of inertia about the x-axis. And M is the bending moment. Let's put some numbers to the test here. Let's say that the moment of inertia of the steel beam is 1,524 inches to the fourth. And let's put some dimensions down. We'll say that the depth of our beam is 16 inches. So C will be 8 inches because it's going to be half of the distance to the top fiber. And let's calculate the stress. Well, the section modulus, which is defined as I over C, is 1524 divided by 8. And let's see what that calculates out to be. So 1524 divided by 8 is 190.5 inches cubed. And so if we have a bending moment, what's the maximum bending moment that that beam can accept? Well, if my yield stress is 36 KSI, we can calculate what the capacity of that beam is. And I'll explain that. I'm going to use the yield stress for right now. So going back to our equation, if M is our bending moment, our stress is M over S, or M over I divided by C, where section modulus is just the moment of inertia divided by the C value. So this number, for right now, let's use it using the yield stress, and that'll tell us our yield moment. So our yield moment, which equal the yield stress times the section modulus. So our yield moment will equal 36 KSI times the section modulus, which we calculated as 190.5. So 36 times 190.5 is 68.58. And let's make sure we check our units. That would be in inch kips. But that's a yield moment. And remember that we never want to reach yield. Let's go back to the stress strain curve. Remember that whenever we yield, we've reached this point in the stress strain curve. That's too high. All the structures that we design are designed somewhere down in here, which is the design load. The design load is always less than the yield load by a factor of safety. And that factor of safety, which varies on structure to structure, is normally, for structural engineers, is always a minimum of 2. It could be higher than 2, but generally is always less, at least 2. So this is the yield moment. That would be the stress at which the steel would actually begin to yield. If we were to use an actual design load, and the design load comes from the steel manual, and I'll be showing you how to use portions of that steel manual in the next module, but just as a prelude, the bending stress from the steel module for a typical beam is going to be 0.66 times Fy. So for 36 KSI steel, if we use 0.66 times 36, that comes in at about 23.76 KSI. We can approximate that to 23 KSI. Many times we just use 24, but we use 23 for this example. Then my design moment, allowable design moment, going back to this equation, I replace this with 23 times 190.5. So then if I calculate the design moment, it's 23 times 190.5. I get 4381.5 inch kips. You can see that that value is lower than the yield moment, which it should be. And that's because of the factor of safety. We want all of our structures designed down here. We don't want to ever be close to this point, and we never want to go past that point. If we go past that point, the structure will have failed. Steel, though, gives us quite a bit of capacity. Our rupture strain, our point way out here, is normally on the order of 5%. This point, the yield point, is normally at 0.02%. Or 0.2%, or 0.002 strain. We're going to look at some examples in the next module using the steel manual, and I'll show you how you can solve these problems really fast using tables. For that, I'll conclude this module, and thank you.